There are lots of chemical projects that are simulated by ANSYS Fluent software using CFD methods. This CFD training package includes 7 different products related to the chemical engineering field, such as pool boiling, diesel fuel combustion in gas turbine combustion chamber, distillation column tray, air gap membrane distillation or AGMD, mixer tank biomass combustion, and also the surface evaporation. By clicking on the subscribe button, you will be informed about the newest CFD training videos by MR-CFD. Or if you are watching the training video, click on the MR-CFD logo and subscribe.
In this project, we will numerically validate the data obtained by the paper named A Numerical Investigation of the Effect of Surface Wettability on Boiling Curve. The geometry of the project consists of a 2D channel, and it is modeled using ANSYS Design Modeler software. Under the General Setup tab, you can see different buttons from scales to units. By clicking on the scale, now in the Appear window, which shows you the names of the different parts of your geometry, you can click and select each part and then click on Display so that the software will show you that part. After double-clicking on the initialization button, a new window will appear showing you different methods of initialization, hybrid and standard. Now in the standard initialization method, you get to choose the first amounts and values for the first iteration of the simulation progress. These values refers to the values used in the first iteration of the simulation progress, and if you choose the values for each parameter wisely, your simulation progress will finish sooner. It should be mentioned that you can also choose the first values or the initial values by just clicking on the Compute From drop-down list and clicking on one boundary. For example, by clicking on Compute From All Zones, the software will automatically average the values in different zones and boundaries and put those values in the initial values for the software. And in this slide, you can easily see the pressure distribution inside our computational domain, and you can easily see how the pressure has built up near the heated wall zone. Now in this slide, you can easily see the velocity distribution inside our computational domain and how the velocity of our fluid has changed after the bubble has moved up. And finally, in this slide, you can easily see the outlines of bubble and how it has moved from the heated wall section to the upper part of our computational domain. And finally, in this slide, you can see that we have extracted the figure 8 of the paper, which shows the heat fluxes of the heat boundary over different delta T axes. And in this project, we have validated the results obtained by the paper for delta T axis equal to 30 degrees. And you can easily see the errors we have calculated for our simulation comparing to the results obtained by the paper. Finally, a summary of different settings and setup that we have used in our project is presented to you in the slide. In this project, we will simulate diesel fuel combustion in a gas turbine combustion chamber. Now, there are several assumptions made in this project. The first one is that the type of our solver is said to be pressure-based since we are dealing with incompressible flows. Also, the velocity formulation is taken to be in absolute form. About the time study, we have selected the steady time study since we want our results to not be as a function of time. Again, under the thermal tab, you can see that the fuel enters a computational domain with a temperature of 300 Kelvin. And now, as for the species tab, you can see that the species mass fraction defined for this boundary is that the fuel mass fraction is equal to 1. There are two ways to check that your simulation process have reached convergence. Alongside the checking the residuals reaching and nearing the 0, you may define some report to make sure that an equation have reached convergence. For example, by just right-clicking on the report definition, going on the new, you are able to choose between different reports. For example, you can define a mass flow rate report on a arbitrary boundary based on your geometry and your simulation. You are able to see whether this mass flow has reached a constant value or not. If yes, it may be a sign that your simulation has reached convergence. but the residual must be checked as well. Now in this 3D contour, you can easily see how the temperature inside the geometry has increased after the combustion process has initiated. Now in this 2D contour, you can easily see how the fuel mass fraction has distributed inside the computational domain. You can easily see the mass fraction of fuel has the highest value after just leaving the fuel nozzle, and after entering the combustion zone, the fuel mass fraction decreases. Finally, a summary of different settings and setup that we have used in our project is presented to you in the slide. In this project, we will simulate the distillation column tray two-phase flow process. Also, by clicking on report quality, again in the console tab, the Fluent software will give you the quality report for your mesh. For example, you can see the maximum aspect ratio of your mesh, maximum orthogonal quality, and etc. There are several assumptions taken into account for this project. The first one is that the type of our solver is defined to be pressure-based, since we are dealing with incompressible flows. As for the velocity formulation, we have taken the absolute format. And as for the time study, we have selected the steady time study, since we didn't want our results to be a function of time. We have also enabled the gravity, and the amount of gravity is equal to minus 9.81 in z direction. Now after expanding the fluid under the material section, you can see that two materials of air and water have been defined. Now in order to define or add a new material, just have to right click on the fluid and then select new. After selecting the water phase in the period window, you can see that the mass flow rate defined for this boundary is defined to be equal to 4 kilograms per second. As for the gas outlet boundary, after clicking on edit button, the most important thing that we should pay attention to in this window is that the gauge pressure actually is defined to be 0, which means that the fluid flow will exit this boundary to the atmosphere. We may also change the under relaxation factors. These factors may be between 0 and 1. Based on the simulation and the project we are doing, we may change these under relaxation factors. But remember that the values set in here are the recommended values for the project, and we highly recommend you to not change these values. Now finally, in order to extract a 3D contour, all we have to do is to click on volume rendering button and accept the appear window. After that, just like the previous slide, a new part will appear on the low left side of the software window. Again, in front of the variable section, we select, for example, water volume fraction, and then click on apply button. Now in this contour, which is the water volume fraction contour, you can see how the water has entered the computational domain and has accumulated on the tray, and you can see how the water has flowed downward through the holes on the tray. Finally, a summary of different settings and setup that we have used in our project is presented to you in the slide. In this project, we will validate the data provided by the paper named Numerical Investigation of Air Gap Membrane Distillation Seeking Optimal Performance. Now in this slide, you can see that the figure 2 of the paper has been extracted, and you can see the picture of the model implemented in the paper. The working mechanism of this membrane distillation system is such that the flow of hot salt water enters its chamber from one side and the flow of cold water enters it from the other side, so that the membrane in the form of filter as well as an air gap is placed in the space between these two streams. The saline feed water passing through its common surface with its adjacent membrane gives off its heat to the membrane environment and then is converted to pure vapor inside the membrane. This steam then passes through the porous medium and enters the air in the air gap with its high temperature. Eventually, these vapors collide with the cold surface of the space for passage of cold water flow, and by losing their heat, they distill and turn into pure fresh water. It is assumed that the water flow inside the model has a Reynolds equal to 100, and consequently, the inlet velocity of the hot salt water flow, the airflow, and the cold water flow has an inlet velocity of 0.1 meter per second. But the direction of salt water flow is from left to right, and the direction of air and cold water flow is from right to left. Now in the Appear window, which shows you the names of the different parts of your geometry, you can click and select each part and then click on Display so that the software will show you that part. Also, if you expand the solid section, you can see that PVDF is also being defined, which will be used as the membrane material. Now in this section, all you have to do is to assign the matching material for each zone, except for the membrane zone. Now in this slide, you can see that the figure 2 of the paper has been extracted, and you can see the picture of the model implemented in the paper. The working mechanism of this membrane distillation system is such that the flow of hot salt water enters its chamber from one side and the flow of cold water enters it from the other side, so that the membrane in the form of filter as well as an air gap is placed in the space between these two streams. The saline feed water passing through its common surface with its adjacent membrane gives off its heat to the membrane environment and then is converted to pure vapor inside the membrane. This steam then passes through the porous medium and enters the air in the air gap with its high temperature. Eventually, these vapors collide with the cold surface of the space for passage of cold water flow, and by losing their heat, they distill and turn into pure fresh water. It is assumed that the water flow inside the model has a Reynolds equal to 100, and consequently, the inlet velocity of the hot salt water flow, the airflow, and the cold water flow has an inlet velocity of 0.1 meter per second. But the direction of salt water flow is from left to right, and the direction of air and cold water flow is from right to left. As was mentioned in previous slides about the 6 different reports under the reports definition section, these reports are used in order to calculate the temperature inside our geometry. For example, if you double click on the point 0.15 report, a new window will appear. In the Appear window, if you click on Compute button, in the Console tab, the software will give you a temperature for that point. Now that point refers to the point in the previous graph with the spatial value of 0.15. It should only be mentioned that point reports give you the temperature on the membrane boundary, whereas the line reports give you the temperature on the bulk. Now in this slide, we brought to you the table which compares our CFD results with the CFD results obtained by the paper. Now in this table, you can see that two sections of 0.1 and 0.15 are specifically designated, which we have calculated their temperature in previous slides. It should only be pointed out that the results in this table have the unit of centigrade, whereas the result we have obtained in previous slides had the unit of Kelvin. The only thing you should do is to change their unit from Kelvin to centigrade, and then you are able to compare the results in this table together. Finally, the summary of different settings and setup that we have used in our project is presented to you in the slide.
In this project, a tank mixer is modeled and the effect of its rotating impeller on the mixing procedure is investigated. The geometry of this project includes a tank and mixer consisting of a rod and an impeller. The geometry is designed in the ANSYS design modeler and meshed by ANSYS meshing. The mesh type used for this geometry is unstructured. The present simulation and its results are considered to be steady and do not change as a function of time. The implicit formulation is more stable than the explicit, and the solution convergence is also easier. In the viscose model, the standard K-epsilon model has been used. That is a two-equation turbulence model that allows the determination of both a turbulent length and time scale by solving two separate transport equations. The standard K-epsilon model is in ANSYS Fluent falls within this class of models and has become the workhorse of practical engineering flow calculations in the time since it was proposed. Robustness, economy, and reasonable accuracy for a wide range of turbulence flows explain its popularity in industrial flow and heat transfer simulations. Also, it is a semi-empirical model. The standard K-epsilon model is a model based on model transport equations for the turbulence kinetic energy, K, and its dissipation rate, epsilon. The model transport equation for K is derived from the exact equation, while the model transport equation for epsilon was obtained using physical reasoning in the derivation of the K epsilon model. The assumption is that the flow is fully turbulent and the effect of molecular viscosity are negligible. The standard K epsilon model is therefore valid only for fully turbulent flows. And finally, we set the rotational velocity equal to 10 rounds per minute. As it is obvious, at the boundary of the sand inlet, that is the type of mass flow inlet, the mass flow rate of the both phases of air and also the water is equal to 0. This is the interface zone, and the type of boundary condition is set equal to interface. Here is the mixture phase. The applied settings are recapitulated in the following tables as a review. The present problem simulates the combustion process inside a gasifier chamber. Via the mesh display section, we can display all the edges and boundaries, including air and fuel inlet, gas outlet, and also the walls. As we are investigating and studying the combustion phenomena, so the energy equation should be activated. In the present model, the discrete phase model or DPM is used because the fuel is injected particle by particle into the internal space of the gasifier chamber in a discrete state to perform the combustion process. This type of discrete phase is used to interact with the continuous phase, and particle tracking is performed with a time step of 0.001 second. Also, the physical state of the discrete phase is a two-way turbulent coupling. The air inlet boundary condition type is mass flow inlet. The internal emissivity, as it is mentioned before, is equal to 1 in both inlets. The gasifier chamber wall is defined as a stationary wall with no slip. For the wall, the boundary condition type for the discrete phase is equal to reflect, despite the inlet and outlet boundary condition discrete phase type that it was equal to the escape. The wall boundary condition type is reflect, that reflect all the particles that collides the wall. After clicking on the initialization button, we go to the last part of the simulation, that is running the calculation. Finally, this table is a summary of the steps for defining the problem and its solution as a review.
In this project, we will simulate the surface evaporation of a falling water droplet. The two-dimensional geometry of the present project is designed using Design Modeler software. The specific airflow domain is designed as a plane with the dimensions of 3 cm by 30 cm. By clicking on Check button, you will see that under the Console tab, the Fluent software will start to check your mesh for any errors. Now, there are several assumptions taken into account for this project. First, the type of our solver is defined to be pressure-based since we are dealing with incompressible flows. As for the velocity formulation, we have selected the absolute format, and as for the time study, we have selected transient time study since we are dealing with a time progressing phenomenon. Also, as was previously mentioned, we have a two-dimensional geometry, so we have selected the planar 2D space. And also you can see here that we have enabled the gravity since the falling process is dependent on the gravity, and the value of gravity is equal to -9.81 in y direction. Now, if you click on the Phases tab, you can see that 3 phases of air, water, and vapor are defined. It should only be pointed out that these phases were previously defined in Materials section. So in order to add a phase here, first you have to define those materials in the Materials section, and then using Add Phase button, you can add your desired phase here. After loading the UDF, under the Mechanism, we select User Defined, and in front of that section we click on Edit button and then select our UDF. Now, as was previously mentioned, if you expand the fluid, you can see that 3 phases of air, water, and water vapor are defined here. If you double click on the first report, in the appeared window you can see that a volume average report type is defined over the fill variable of volume fractions of vapor phase. Now, after initializing the software, you can see that the value for water and vapor volume fraction are defined as 0. Now we need to define the position of the droplet for the software. To do that, we click on Domain Ribbon tab. In the new window, under the Shape section, we select Circle, and under X and Y and Radius section, we define the initializing position and radius of the droplet. Now in this slide, you can easily see that the initial position and shape of the droplet are defined correctly. Now in this contour, which is related to the last time step of our simulation, you can see that the droplet is completely evaporated. And in this contour, you can easily see the velocity distribution inside our computational domain for the mixture. Finally, a summary of different settings and setup that we have used in our project is presented to you in the slide.
Obtain the mesh file and also the full training movie by purchasing this product. To benefit from MR-CFD services including simulation, consultation, and training, contact our experts via info@mrcfd.com.